Hello everyone, I am Sumedha. I am from MSc Chemistry first year. Today I am going to read the Organic Chemistry Unit 3, which is Reaction Mechanism. Types of mechanism, structure and reactivity. First is substrate and reagent. A substrate is the substance on which a chemical reaction takes place, and reagent is the chemical which reacts with the substrate to bring about that reaction. Molecularity, it is the number of reactants molecules that colloid simultaneously to bring about a chemical reaction. Electrophilic and nucleophilic reaction, a reaction in which an electrophile electron loving species attacks a molecule or ion is called an electrophilic reaction. A reaction in which a nucleophile nucleus loving species attack a molecule or ion is called a nucleophilic reaction. Leaving group, a leaving group is an atom or group of atoms that detach from the main molecules during a chemical reaction, taking with it the bonding electrons. Reaction intermediates, a reaction intermediate is a short-lived unstable species that is formed during a chemical reaction but does not appear in final product. Transition state. A transition state is a highly unstable state of a chemical reaction where old bonds are partially broken and new bonds are partially formed. Types of reaction. Substitution reaction. It is defined as a chemical change where one functional group in an organic compound is displaced by another functional group. These reactions are classified into three categories: electrophilic substitution, nucleophilic substitution, and radial substitution. Addition reaction. It is a type of chemical reaction in which two or more molecules combine to form one large molecule. Third is elimination reaction. It is a type of chemical reaction in which two atoms are removed from a molecule and as a result a double bond or triple bond is formed. Rearrangement reaction. It is a type of chemical reaction in which the structure of molecules changes by shifting of atoms or bonds within the same molecule. Redox reaction. A redox reaction is a chemical reaction in which oxidation and reduction takes place simultaneously. Thermodynamic and kinetic requirements. A reaction takes place spontaneously if the magnitude del G is negative or GF reactants is greater than del GF products. Free energy change of a reaction depends upon del H2, del S and T and the given by the thermodynamic reaction. Del G is equal to del H minus T del S. Del G is equal to minus T minus R T ln K. Possibilities of reaction take place or not. If del H positive or del S positive, then del H is smaller than T del S. Del G is negative. Reaction possible at high temperature. If del H is positive or del S negative, then del G is positive. This reaction is not possible. If del H is negative, del S is positive, del G is negative, then this reaction may be possible. If del H is negative, del S is negative, del H is equal to TdS at low temperature. Kinetic requirements. It is depend upon the activation energy. If the activation energy barrier is low, then the reaction will take place at high speed. If activation energy barrier is high, the substrate react slowly and will take very long time to complete. EA is equal to del G is equal to del H minus T del S. Del G is equal to 2.303 RT log KEQ, where K is equal to AC minus EA upon RT. K is rate constant, R is gas constant, E is activation energy and T is temperature. Kinetic and thermodynamic control. When a reaction produces more than one product and the product that formed most rapidly called kinetic product. Reaction that produce the kinetic product as the major product are called kinetically controlled. When a reaction is under kinetic control, the amount of product depends on the rates at which they are formed. Most stable product is called thermodynamic product. Reaction that produce the thermodynamic product as major product are called thermodynamic controlled reaction. For example, reaction of 1,3-butadiene with 1 equivalent of HBr, CH2 double bond CH double bond CH2 plus HBr, then it gives at minus 80 degrees Celsius CH3 CHBr CH3 double bond CH2 plus it is 80% plus CH3 CH double bond CH2Br it is 20%. And the other product will be CH3 CHBr CH double bond CH2 it is 20% and CH3 CH double bond CH2Br it is 80%. Reactants at low temperature kinetic product and irreversible process take place. At high temperature thermodynamic product and reversible processes take place. Hammond's postulate. It states that the transition state of a reaction resembles the structure of the species, reactant or product to which it is closer in energy. Significance of Hammond's postulate. Hammond's postulate tells us about the geometry of the molecule. Limitations. It is not always possible to predict the geometry of transition state with reactant and product. Curtin-Hammett principle. When a reaction involves two rapidly interconverting intermediates that form different irreversible products, the ratio of products depend on the energy difference between the transition states and not the ratio of the intermediates themselves. The equilibrium constant K will be K is equal to B by A. The formation rate of C is equal to dC by dt is equal to KCA. dt by dt is equal to KdB. And dd by dt into dt by dc is equal to KdB by KCA. dd by dc is equal to KdB upon KCA. Using the value of B by A from equation 1, we get dc by dt is equal to KD by KC into K. From chemical kinetics, that K is equal to E minus del Z naught upon RT, which is equation 3rd. Kc is equal to RT by NH E minus del G naught A by RT. Kd is equal to RT by NH E minus del G naught B by RT. This is equation 5. Using equation 3 and 5 in equation 2, we will get d by dc is equal to RT by NH E minus del G B star upon RT by NH E minus del G star A upon RT into E minus del G naught by RT. d by dc product ratio is equal to E minus del G star B by RT plus del G star A by RT E minus del G naught by RT. Product ratio is equal to E minus del G star B plus del G star A minus del G naught by RT minus del G B star plus del G star A minus del G naught is equal to minus del G star. Product ratio is equal to E minus del G star by RT. Potential energy diagram, transition state intermediate. A potential energy diagram shows how the energy of molecules changes during a chemical reaction from reactants to product. The transition state is the highest energy point in the curve. An intermediate forms between two steps in a multi-step reactions. The transition state is the highest energy point in the curve. An intermediate forms between two steps in a multi-step reaction. Potential energy diagram of reactions with reactant, product and transition state. A typical potential energy diagram of endothermic and exothermic reaction products and transition states. Potential energy diagram of reactions with reactant, product transition state and intermediate. It is a typical exothermic reaction with reactant, product, intermediate and transition state. Methods of determining a mechanism. The steps through which a complex reaction takes is called the mechanism of a reaction. Product analysis. The mechanism of a reaction can be determined by the identification of products and determining their relative amount. Crossover experiment. Crossover experiments are quite useful in the determining whether a particular reaction is a one step or a two step process. Isolation, detection and trapping of intermediates. Isolation. It involves separating and purifying a stable intermediate from the reaction mixture. Detection. It uses technique like spectroscopy to identify the intermediate spectroscopically. Trapping. A chemical technique used to study short-lived unstable molecules that are involved in a reaction. Isotopic labeling. The mechanism of many reactions can be studied by using molecules in which an atom is substituted by its isotope. Kinetic studies investigate the rate of a process and the factors that influence it, such as temperature, catalyst, and concentration. Stereochemical analysis. Stereochemistry is of a reactant and product can also be used to identify the pathway of an organic compound. Isotope effect. The change in a reaction rate when an atom is replaced by one of its isotopes. K1 E is equal to K1 by KH. K1E is kinetics isotope effect. If the replacement of an atom by its isotope is involved in the rate determining step of the reaction is called primary isotope effect. The reaction in which there occur no CH cleavage, even the rate of reaction changes to a small extent on replacing H atom by D atoms or T atoms is called secondary isotope effect. Generation, structure, stability and reactivity of carbocations. A carbocation is a positively charged carbon species. It forms when a carbon atom loses one of its bonding electrons, usually during a reaction. Common methods of generation. First is hydrolytic bond cleavage, second is protonation of alkenes, third is ionization of alcohols. Structure of carbocations. The carbon atom with a positive charge has 6 electrons in its valence shell. It is sp2 hybridized. It has a planar structure. Bond angle is about 120 degree. The empty p orbitals lie perpendicular to the plane. Stability of carbocation. It depends on how well the positive charge is stabilized. First, tertiary is greater than secondary, is greater than primary and greater than methyl. Reason for stability plus I effect. Alkyl group donate electron density to positively charged carbons. Hyperconjugation, delocalized of electrons from CH bonds of neighboring atom to the empty of p orbitals. Resonance stabilization. If the positive charge is delocalized over several atoms, stability increases. Benzyl allyl is greater than tertiary, is greater than secondary, is greater than primary, is greater than methyl. Reactivity of carbocations. Carbocations are highly reactive intermediates. They are electrophilic and react with nucleophiles. Their reactivity is inverse to stability. Methyl is greater than primary, is greater than secondary, is greater than tertiary, is greater than benzyl. Generation, stability, structure and reactivity of carboanions. Generation. A carboanion is a negatively charged carbon species. It forms when a carbon atom gains an extra pair of electrons or when a bond breaks hydrolytically, leaving the electrons on carbon. Common method of generation by hydrolytic bond cleavage, by deprotonation of weak acid, by reaction of organometallic compounds. Structure. The negatively charged carbon atom has 8 valence electrons, 6 plus 2 extra. It is sp3 hybridized. It has trigonal pyramidal shape. It has one lone pair of electrons. Stability. It depends on how easily the negative charge delocalized or stabilized. Methyl is greater than primary, is greater than secondary, greater than tertiary. Reactivity. Carboanions are nucleophilic. They react with electrophiles. Reactivity is inverse to stability. Tertiary is greater than secondary, is greater than primary, is greater than benzyl or allyl. Generation, structure, stability, and reactivity of free radical. Generation. The homolytic cleavage of covalent bond is responsible for the generation of most of free radical species. First is thermal cleavage, second is photochemical cleavage. Structure of free radical. It has trigonal planar geometry. It is sp2 hybridized, three hybrid orbitals oriented at 120 degree in plane perpendicular. Stability of free radicals. Stability of free radicals will increase as the number of donating group attach increases. The stability order is as benzyl or allyl is greater than tertiary, is greater than secondary, is greater than primary, is greater than methyl. Reactivity of free radical. They are highly reactive because they contain an unpaired electron. They can act as electrophiles or nucleophiles. Reactivity is inverse to stability. CH3 is greater than primary, is greater than secondary, is greater than tertiary, is greater than benzyl or allyl. Generation, structure, reactivity, and stability of carbenes and nitrines. Carbene are the chemical species that carries two non-bonding electrons, paired or unpaired, on the carbon with total of 6 valence electrons. Generation methods from diazo compounds, from chloroforms and base, from photolysis of ketones. Structure of carbenes. It can exist in two forms depending on the spins of electrons. Stability of carbenes. The triplet carbenes are generally more stable than singlet carbenes. Stabilization by substituents. Alkyl groups stabilize carbenes by plus I effect and hyperconjugation. Reactivity of carbenes. They are highly reactive intermediates. They are electrophilic in nature. Reactions. Addition to double bonds, insertion into CH or XH bonds, rearrangement reaction. Nitrines. It is a neutral species containing a monovalent nitrogen atom with 6 valence electrons. Methods of generation: from azides, from isocyanates, from amides or haloamines. Structures like carbenes, nitrines also exist in two forms, singlet or triplet. They are sp2 hybridized. Stability of nitrines. Triplet nitrines are generally more stable than singlet due to less electron-electron repulsion. Stability increase if the nitrogen is attached to the electron donating groups. Reactivity of nitrines. Nitrines are highly reactive intermediates. They can act as both electrophilic and nucleophilic. Reactions: insertion into CH or NH bonds, addition to double bonds, rearrangement reaction forming amines or isocyanates. Effect of structure on reactivity. Reactivity. It is defined as the tendency of organic compounds or substance to undergo chemical reaction either by itself or with other substance, often with release of energy. Structural factors influencing reactivity include as a functional group. The inductive effect is the shift of electrons through sigma bonds in the molecule due to the electronegativity difference between atoms. Resonance effect. The resonance effect occurs when electrons are delocalized through pi bonds and lone pairs in a molecule. Hyperconjugation. It is interaction between sigma bonds and an empty or partially filled p orbitals or pi orbitals on an adjacent atom. Steric effect. It happens when a big group, atom or molecule, are too close to each other and they push or block each other because of crowding. Aromaticity. It is a specific stability shown by some ring-shaped molecules because of the movement of electrons inside the ring. Bond strength and energy levels. Bond length is the distance between the centers of two bonded atoms. Is bond strength. When two atoms come close to form a bond, their energy decreases. Is energy level. The Hammett equation and linear free energy relationship. The Hammett equation. It is the first attempt to give numerical values for the quantitative treatment of structure on reactivity. Hammett proposed the equation for cases of meta and para x C6H4y as given below. Log k upon k naught is equal to sigma upon sigma into. It is the first attempt to give numerical values for the quantitative treatment of structure on reactivity. Hammett proposed the equation for cases of meta and para x C6H4y as given below. Log k upon k naught is equal to sigma into rho, where k and k naught are constant for group x which is not equal to h, or x may be equal to h. Sigma and rho are constant for the reaction condition and substituent x respectively. Derivation of Hammett equation. Hydrolysis of a series is required which is as x C6H4COOH plus H2O gives 2 x C6H4COO negative plus H3O positive. X is constituent at meta or para position. Ka is dissociation constant. Sigma x is equal to logarithm of Ka minus logarithm of Ka naught is equal to minus Pka plus Pka naught, where sigma x or sigma called as substituent constant using logarithm m minus logarithm n is equal to logarithm m upon n. Equation rewrite as logarithm of Ka upon Ka naught is equal to sigma. Rho is equal to logarithm of Ka upon Ka naught upon K upon logarithm of K upon K naught. Rho into logarithm of K upon K naught is equal to logarithm of K upon K naught. We know that logarithm of K is equal upon logarithm of K naught is equal to sigma, and logarithm of K upon K naught is equal to rho sigma. For any equation, logarithm of K is equal to rho sigma minus logarithm of K naught. Rho is equal to logarithm of K upon K naught upon logarithm of K upon K naught. Logarithm of K upon K naught is equal to rho sigma. Logarithm of K is equal to rho sigma minus logarithm of K naught. Result given by equation 1, 2, 4 and 5 are called Hammett's equation. Linear free energy relationship. Rate constant K for typical reaction. K is equal to RT upon NH E minus del G star upon RT, where del G star is free energy change of activation step at temperature T. For K naught is equal to RT by NH E minus del G naught T del star Z naught upon RT. Put equation 1 and 2 in Hammett's equation. Logarithm of RT upon NH E minus del G star upon RT upon NH E minus del G star naught upon RT is equal to sigma rho. Logarithm of E minus del G star upon RT upon E minus del G star naught upon RT is equal to sigma rho. Multiplying both equation by 2.303, we have 2.303 log E minus del G star upon RT E minus del G star naught upon RT is equal to 2.303 sigma rho. Logarithm of E minus del G star upon RT upon E minus del G star naught upon RT is equal to 2.303 sigma rho. Logarithm of E minus del G star upon RT minus ln logarithm of E minus del G star naught upon RT is equal to 2.303 sigma rho. Minus del G star upon RT ln E minus del G naught star upon RT ln E is equal to 2.303 sigma rho. Minus del G star upon RT plus del G naught star upon RT is equal to 2.303 sigma rho, which implies del G star naught upon RT minus del G star upon RT is equal to 2.303 sigma rho. Del G naught star minus del G star upon RT is equal to 2.303 sigma rho. Del G naught star minus del G star is equal to 2.303 RT sigma rho minus del G star is equal to 2.303 RT sigma rho minus del G star naught. Taft equation. The Taft equation is the linear free energy relationship used to correlate and predict rates and equilibria of aliphatic reaction. It is especially useful where Hammett equation fails. For example, for either aliphatic systems, Hammett is for aromatic substitution. Why Taft equation was introduced? Hammett equation works only for when substituents affect a reaction through resonance and inductive effect via an aromatic ring. But in aliphatic, resonance effects are negligible and steric effects become very important. Thus, Taft introduced parameter to separate polar inductive effect and steric effect. Original form of Taft equation for reaction where steric effect are minimal. Logarithm of k upon k naught is equal to rho star into sigma star. K is equal to rate constant for substituted compound. K naught is rate constant for unsubstituted reference. Sigma star is Taft polar substituent constant and rho star is reaction constant. Steric effect equation for reaction denominated by steric effect is logarithm of k upon k naught is equal to ES. ES is Taft steric substituent constant. ES is Taft steric substituent constant. Delta is the reaction constant for steric sensitivity. Full Taft equation, dual parameters equation. Many reaction involves both polar and steric effects, so Taft combined both terms. Logarithm of k upon k naught is equal to rho star sigma star plus del ES. It is used for ester hydrolysis nucleophilic substitution in aliphatic systems. Thank you.